Yeah, thanks for showing up today. That's great. Great to see a large crowd like that. By training, I'm a structural geologist. So I'm not a geophysicist, I'm not a geochemist, and I haven't discovered an ore body. Okay, so advancing the discovery of hidden ore bodies. What can we as GSWA contribute to that? Well, as you've seen before in previous talks, we acquire large-scale pre-competitive geodata sets, passive seismic MT, active source reflection surveys, and geophysics, and of course, all the potential field data as well. We also, and that's very successful, do geochemical isotopic mapping, we do geochronology and so forth. And the extra value we can add is integrate these in the framework of geological processes. And it's important for us to remember when we look for mineralization and ore deposits, they're actually a byproduct of crustal evolution and reworking. Geodynamics, the purpose of geodynamics is to run the planet and not to form ore deposits, right? So if we don't understand the processes, it's going to be hard, I think. So in this presentation, I will show some highlights. I'll highlight some parallels between large-scale features between the Pilbara and the Yilgarn Craton, and they speak to some of the issues that we've seen before, that upper crustal structure and lower crustal structure or lithospheric structure, they're often not aligned. So I'll try to explore why that is and what we can learn from that. Okay, so going back to one of the approaches to attack mineral systems and to find mineral deposits. One example, 2002 was the end of the AGCRC and the beginning of the PMD-CRC, both large incorporated research centers that were focused on understanding the geodynamics of ore deposits. And the 5 questions came out of that. And the idea of the 5 questions was to understand the background of, or the geodynamic setting, or the whole processes that are involved in mineral systems. Now, as the Geological Survey, we can really make big contributions to 2 of those. And this is about architecture and tectonic history. So trying to answer or contribute to the questions, what are the structural and geological characteristics of the mineral systems? And what's the overall tectonic architecture and the tectonic history of those? So one of the things that have worked out really well in the last few years was systematic mapping of granites and greenstone. So this is an example of a paper we had in geology a few years ago. And it came to a very surprising conclusion, something we had seen on maps before. I mean, everyone knows if you look at maps long enough, you can see all kinds of things in geological maps. But what we saw was there were large-scale trends that were cutting across the interpreted tectonic units of the Yilgarn Craton. Basically, the terrain boundaries that were proposed before. So, that's really puzzling. And here, what you could see is the strontium over yttrium ratio. That's not only a pathfinder for mineralization, but it also gives you the depth of melting of the source, or the depth of the source of the granites. So this is a granite geochemistry data set. I think we have now nearly 9,000 data points across the Yilgarn Craton. So this is the ones we used at the time, and these are only it's only a subset of those. So this is really puzzling. How does it work, and why are these structures there? And also, what does it mean for the geodynamic models? If they cut across the Ida fault, then it's very unlikely to be an accretionary terrain boundary. So that's a problem for many of the models that have been proposed before. And so Ruth has shown some of those, the right and the middle slide before. And so basically, the WA array has confirmed that pattern that we see. So we can see that the crustal thickness in that southern strip of the Yilgarn is a lot larger than in other parts. And also the VP over VS ratio, VPVS ratio is different. So what VPVS ratio can be interpreted as how mafic or how juvenile the crust is. So there's a compositional difference between that southern strip of the Yilgarn Craton compared to the central part of it. So, and again, this goes across the terrain boundaries that have been interpreted from the potential field data in the upper crust. So if we look at this in more detail, and this is also going to be in the report that has been about to be released soon, report 256 from WA Array. So I'm showing you two cross sections. This is one that goes through the you and me terrain here, and I think this is the south. This is northwest and southeast. So you can see that there are actually a lot of variations. So this is the relative shear wave velocity. So basically, you assume a crustal model where the shear wave velocity increases with depth. That's normal. And then this has been the actual data is subtracted from that, so you are left with an anomaly. And what I want you to take away from this is that there's a real a long strike variation in crustal velocities which come back to compositional differences between those different areas. And the same you can see if you go through the corrosion tectonic zone. Even within the corrosion tectonic zone, this is not homogeneous. Okay, so we have large along strike variations in these terrains. So that's all very well. So we have orientations that go pretty much everywhere. But why is that the case? To attempt to answer that question, let's go somewhere else. Let's go to the Pilbara. In the Pilbara, we have also acquired a number of large-scale data sets. One is the end of the seismic line 18 GA-KB1 goes from near Marble Bar all the way almost to the NT border across the Canning Basin. The main purpose of that was to image the Canning Basin and its basement, but also part of it actually went through the East Pilbara terrain. So this is the cutout of that area here. And it cuts across some of the granites and greenstones. Now, taking that, this is one rendition of the seismic as it was shot. So the right-hand side of that is the modified, is this area that has a strong Proterozoic overprint as we approach the Patterson origin. So it's modified, but the left-hand side is is basically almost entirely Mesoarchean in structure. And it's one thing that you can see, it's layered with a low reflectivity upper crust, higher reflectivity in the lower crust. Now with some colleagues from Geological Survey of Canada, Nathan Hayward, and from Simon Fraser University, Andy Calvert, we did some work where we did a 3D gravity version that was constrained by passive seismic data that Huayu had acquired. We had acquired with Huayu in the area. So basically what you can do is you can then paint, if you like, the reflection line with densities. You can see the moho here, and you can see that there's a different character in the Proterozoically modified crust in here. What you can also see, it doesn't actually track very well with the greenstone and with the granite domes and greenstone basins at the surface. And if you look at those lines here, you can see that the mid to lower crust changes quite a bit in character from in the north and the south. So one thing is you have a very, very layered crust that doesn't actually repeat the granite greenstones very well. And on the other hand, you also see that there also are lateral or north-south variations in the composition of the mid to lower crust. One other way of showing the density contrast is depth maps of the density. That's the density from, not the actual density, but it's the density from the inversion. And what you see is that if you are in the shallow crust, you can actually see the dome and basin structure quite well. For reference, the black lines is the outline of the Warrawoona large igneous province rocks. So basically, this is the Mount Edgar Dome. Here's the Corona Downs Dome over here. Warrawoona syncline sitting in here. But as you go deeper, that pattern disappears. So that's interesting in itself, that you have this tens of kilometers sized, iconic dome and basin structure, and actually disappears as you go deeper than 10 kilometers. You can actually not see it anymore very well. But what you see is that that this orientation here, along this orientation, things change. So you have a higher density in the northern part here, and sort of a lower density here. The same becomes apparent at 30 kilometers. As you go below the Moho is actually very shallow in the Pilbara. The situation reverses, and now all of a sudden you have this structure here. And what's common is that there is actually a structural framework. There are orientations that go this way, and there are orientations that go this way. So there's an east-southeast and a north-northwest trend, and that kind of divides up the whole area on a different scale. So basically, the upper crustal dome and basin disappears, and you end up with a larger scale structure. Now, if we look at the granite, okay, this is another image of that, basically an east-northeast trend with north-northeast offshoots, and it's larger than the individual domes. If we look at the granite geochemistry, this is data from the granites, and again, I'm plotting here strontium over yttrium. So the warmer colors are higher values, and so these trends persist as well. So you get some modifications within the domes, but on the larger scale, there are these large-scale trends, and so what we think we see here is an east-northeast trending corridor of lower strontium over yttrium in the granites, which means is a lower pressure melt source. So one way of interpreting that for us is that we think we are looking at a rift system. One of the things in here is that if you look at the ages of the granites in here, they become younger towards the center in the middle, and also there is the youngest bit in here in the Mount Edgar Dome is actually an east-west trending structure, intrusion that is almost in a dilational site to if you were stretching it in this direction, north, northeast, south, southwest. So basically, our model for this is that we are looking at an early rift system that then fragments into rifts and transforms. These are then later reused in the Mesoarchean, where we have less volcanic input, more sedisto-clastic basins, and then they get pushed back together at various events, and they get reactivated time and time again. So why a rift transform system? Well, one of the things in the Pilbara is that we know that prior to the Paleoarchean, there's no record of continental crust. So there's nothing there. So if we form some sort of structure in that time, it has to be in primordial crust, something like a stagnant lit or something like that. So basically, this is probably a primordial mafic crust. It's probably thin, and it starts to rift. And the example we have of thin crust diverging and extending is mid-ocean ridges. So basically, something like a rift transform systems can form, and you would expect to have focused the magmatic activity in both in the rifts and the transforms. And then over time, they alternate in their activation. Why, we don't know, but there's some ideas. So basically, in these fragments, in between these fragmented crust, you form the granite domes and the greenstone basins. The basins become deeper in both the rifts and the transforms. And this is what you then end up with. So this rift transform geometry then sets up the structural framework for subsequent events. The Neo-Archean passive margin that forms in the Fortescue Basin, for instance, would be, a reactivation of the original rift orientation that we see here. The dikes dilate in the transform direction. The Fortescue dikes that cut across the Meso and the Paleo-Archean structure. Let's go back to the Yilgarn. So this is where I throw reason to the wind completely and make a comparison. So what if these structural interferences are typical of other Archean cratons as well? What if, can we use that to possibly explain what's happening in the Yilgarn as well? First, we rotate the Yilgarn in a convenient orientation, the Pilbara, and so we compare these structures. And so basically, what we could postulate, we are looking at primeval rift structures that form early on the Craton evolution, and they form basins, and the basins form a rift that transforms in those situations. These are the transformed, that is secondary structures. And so the primary ones in the Yilgarn would be those east-northeast bands that we see compositionally, whereas the secondary ones are the transforms. They get activated over time, and of course these would be then the orientation where you form things that control the Eastern Goldfield rift system. Right? It doesn't have to be one structure. It could be an array of structures that forms in there. And once you have these orientations, you can of course also load them and dilate them, and then they will form structures that cut across in terms of radial orientations or all kinds of things. Then, as the cratons become thicker and the lithosphere becomes more solid, you then go back and form actual passive margins. These are the Fortescue in the Pilbara Craton and the Albany Fraser and the northern margin towards the Glenberg in the north. So these are the parallels, and that could this is one possibility to explain that. So why does it matter? Well, one of the things, of course, it might not be true at all, right? but I think it gives you something to work with, right? And for us, it's interesting to see, and is it something we can test with more data that we collect? So, the hypothesis here is that we propose is that cratons grow in rifts. The rift transform structures, they form in primordial, and it's not continental crust because there's no continental crust, and it's not oceanic because oceans can only form after continents rift. Okay, so it's mafic primordial crust, and they establish a blueprint, and the structures grow with the craton as the craton becomes bigger over time. And they have the potential for fluid and melt pathways. Just think about, the seafloor systems you can run in those transforms and in the rifts. And if you metamorphose them later, if you reactivate them, they can accumulate alteration and localize melts and fluids. We're not clear what controls the switching between the rifts and the transforms, but the suspicion is that the thermal structure controls the rifting mode. That's a different talk. Sorry. So for the Eastern Goldfields, well, there's an alternative to the terrain accretion model that basically sits on the plate tectonic paradigm. The along strike segmentation may suggest minimal displacement along the north-northwest oriented structures. Many deposits are at the intersection of the R and Ts, and I think we've seen a lot of examples here. We can see a lot of examples in the Eastern Goldfields, and so the array of subbasins. Well, what the complexity of the structure in the Eastern Goldfields could be, it's an array of subbasins that are controlled by the primary structures, and the overall basement could be what JT has talked about, an underlying Yuan-Mi age or Mesoarchean crust. So for the Kalgoorlie area, the idea that there was a mid-crustal detachment from the seismic interpretation previously may not be true. If there are no large displacement accretionary structures, maybe they are just a complex array of different or stacked basin segments. So what's coming soon from us as well is this year we will actually release an array of the reprocessed seismic lines around Kalgoorlie. This include the 7 lines that we shot 5-6 years ago, and also some old GA lines. This is just a teaser here of some of the interpretations by Andy Calvert. He's also got a method where he uses crooked lines to triangulate the reflectors and give you a strike of the reflectors. And, so basically, there's a way of mapping that here, and this is just one of the examples, the lines in the south near Kambalda. But next year, we hopefully will be able to integrate all of these together with the WA array data into 3D models. And I think that's it. Thank you.